Good morning. I don't know, but I think people have been waiting for this game to turn up amongst the games that I was playing for this course. But we're here now with a classic. Although I don't know if this is the classic one, but this is Portal 2, the second one of these games. Portal 1 was a bit of a revolution, I'd say. Oops.
Congratulations, not on the test. Most people emerge from suspension terribly undernourished. I want to congratulate you on beating the odds and somehow managing to pack on a few pounds.
Sick. Yuntron asking about extending the deadline of the assignment? Unfortunately, no, I cannot extend the deadline, especially not into the weekend. It's actually school policy that we don't have deadlines on the weekends.
Do whatever it is you do when you're not destroying this facility.
So the reason we are looking at Portal today is actually this. I can see through this thing to another part of the environment, which means my render is not just stopping at this particular wall. My view from my render is going through that wall, coming out somewhere else, and allowing me to see another part of the scene through it. And it's going back the other direction as well, so it's quite interesting. You can actually put two of these right next to each other. And you're like, oh, I walk in here and I actually came back out. And this is very much like the feeling of having a mirror reflection here, because I've put a portal here and I walk out of this portal and I don't go into a different world, I come back into the same world next to where I was. You can actually see my character just for a little bit through there. I mean, if I get closer, you can actually see the character, so it's like I'm looking at myself moving because the portal allows me to see back into the world that I'm in. What am I actually doing here? Classic puzzle game. Because of all these little mechanics. How do I get over there? Actually, I wonder if this water actually hurts me or not. Oh, it does. It was shallow water in one of the other ones I was doing. You can tell it's been a while since I played this game. Alright. Oh. So that keeps that moving. Right. Okay, so let's do this to get over here. And then we'll do that again to get control of that platform. Oh, I get it. I'm gonna use this block to just... No, I can't block it. I'm gonna have to jump over it.
I'll give you credit. I guess you
There we
are
go.
listening to me. But for the record, you don't have to go that slowly.
Okay. I'm gonna let this go. Very, very interesting game just for the puzzle design mechanics nearly more than anything else. But that ability to reflect vision around to different places is something we're going to talk about today. That's one of the things we're talking about today. Alright. Let's get into the lecture. Jason. Saying, is it possible to extend the gaming session since most of us like games? Well, I did actually in the gap in between term 1 and term 3 do an entire streaming series that I was calling Mark on Mondays that I did on Monday evenings. And there's actually lots of games in that, but there isn't Portal, interestingly enough. I played a lot of other things. Anyway, let's get into it. Okay, so what were we looking at last lecture? Last lecture we started learning about reflections, and we did that using the idea of a reflective object in our scene that then could have vision bounced off it, I guess. So the idealized version of that is the chrome sphere somewhere in our scene. So completely reflective, completely circular, so it goes off in any direction, and we can just reflect our view off that, see what it hits in the scene, and then render whatever color we see somewhere else in our scene. And the joke that was running there, and that wasn't just for reflections, but that was a joke for many different techniques in graphics. It's like, why don't we just use ray tracing instead? And I think that's quite funny because ray tracing is such a clear and simple technique. You know, like it's a simulation of the reality of light in our world, which makes it really easy to have it kind of stand in for any of the techniques that I'm teaching you. But I'm not only going to teach you to use ray tracing because, like, if it's the theory of ray tracing, I've already taught it to you, and the implementation of it is a matter of just sort of would be a matter of like a tutorial to like learn the bits and pieces. But the capability that we have to actually run ray tracing is limited. There are no games that are using ray tracing for their entire illumination model, so their entire lighting model. There are games that are using partial ray tracing for some reflections, partial ray tracing for some, I think maybe some ambient occlusion and things like that, but I think even that is not being done with ray tracing at the moment. I think, if anything, it's mostly just reflections. But even so, today I'm not even, and on Monday I wasn't even teaching you how to necessarily do ray tracing for reflections, because that's actually reasonably simple in terms of like the theory of it. But what I'm teaching you is all of the reactions we have to the fact that ray tracing is too hard to do computationally right now. And as I said, if I was to deliver this again in 5 years' time, maybe I would be talking completely differently. Maybe I wouldn't be talking about reflections at all, because ray trace reflections will have taken over from all the techniques that we're using, because we simply have the computational capability to do it by then. I don't know if 5 years is too short a time to be saying on that, maybe 10 years, but who knows? But I should actually place us in the timeline where we are now, that the use of ray tracing has appeared in computer games. So it's appeared in real time, virtual environments, but it hasn't yet become easy enough or commonplace enough for me to say there's no reason to learn about any other style or form of reflection. So first thing we did was learn about cube maps and sampling cube maps. So we're talking about a box that surrounds us, I mean, I talk about it like it's a fanciful idea, but everyone, well, not everyone, but most people are probably in a room right now. So we know the idea of being surrounded by a box. And if you put a lot of posters up in your room or anything like that, you actually know what it's like to be surrounded in a box that has texture information, color information on it. And you know that any direction you look in, you're going to see some part of the box that you're in. It's very philosophical right there. Anyway, so we looked at environment mapping, which was just using that box and nothing else, and getting reasonable reflections out of that. And it really, really depends on how your scene is built, whether the environment reflection is enough or not. Because we looked at the hilarious thing of Mario 64, where the environment map was built with like a blue sky and this kind of pinky, sort of pinky and black ground underneath. And most of the environments that you're in when you're Metal Mario didn't have that around you, so it looked a little bit odd, but it still gave a strong idea of the effect of you being metal at the time, so it kind of gets away with it. But then we went into, okay, what if we want to make this really, really look right? We could do things like real-time building of the cube map. So we could do 6 renders outwards from our current position, put that all into the textures that are going to be in the box around us. So this isn't necessarily the skybox I was talking about, which is just like the background environment that we can always see, but this was something specific for reflections. And so I was able to pick up other objects in the scene, pick up, say, the character, if there's a model for the character in the scene. A lot of first-person games don't have a character model because they don't need one. What else is it doing? Yeah, it was giving us then the ability to calculate our reflections on exactly what we could see in the scene right then and there. Some of the techniques we're using for that are render to texture and frame buffers. So those techniques are actually pretty common, and we're going to keep using them. So the ability to take a render from a virtual camera within our scene and put that into a texture buffer. So into a color buffer, which we then can use somewhere else in our scene. So we use those to build our cube maps. We also had a bit of a chat about the efficiency of these things, because like when you think about it, if I have to do 6 separate renders just to make the reflection cube map, and then I'm making a 7th render using that cube map to bounce off one reflective object, I'm cutting my frame rate. I'm dividing my frame rate by 7, and there's got to be a problem there, right? That's potentially a huge issue, and there's lots of tricks to try to get around that. But you know, you always go back and watch that lecture if you want to know about those. Okay, so today, what are we covering? We're going to look at reflections again, a little bit more at reflections, and we're going to look at reflections just from planar surfaces. So this is like maybe 2 examples that are super obvious for planar reflections, is a mirror and say a body of water like a lake or something like that. If you get a really pristine still lake, it's like a mirror. You look down on it and your vision bounces straight off. I mean, like your vision is like a moving object, but it's not, you know, but you get what I mean. So we're looking at direct reflections of flat surfaces, as opposed to direct reflections off an arbitrary curved surface that we did last lecture. And it's quite funny actually when you think about it, because this is the easier form of it if I'm reflecting off a flat surface. But it's interesting to look at, because if we think it's an easier form, then we instinctively try to do less processing to make it work. So we're gonna talk about that and look at how that works. The next thing we're going to do is an extension not of reflections, but an extension of the technical techniques that we used for reflections, which is using these frame buffers that we've been making to do something called post-processing. Post-processing is a big umbrella term. There are many, many techniques in post-processing, but they refer to the idea that we can render an entire scene, right? So what we can do is decide already what color of all the pixels are that we want to display on our screen, but then do something to them afterwards. So we kind of interrupt the process after the fragment shader is finished. So we let the fragment shader finish, write everything to not necessarily the main frame buffer this time, but a secondary frame buffer, which is storing the screen before it goes to the main frame buffer, and in between those two we can do something else. So we'll talk about that in a second. One question that I had on Monday was, what about sphere maps? So I went through, had a look. I have not really done much work with sphere maps. I've seen cube maps more often and sphere maps, so I said, okay, I'll do some reading and I'll do some analysis and stuff and talk to you a little about, just quickly at the start of this lecture, about sphere maps, because the question was, sphere maps are a thing. People have obviously used them. Can we talk about the difference between them and cube maps, for example? So a sphere map is a single texture, whereas a cube map was 6 textures, one in every direction. The sphere map was this idea. This is not... Actually, no, this is a map. This is a sphere map. But it's created with a photograph taken in a spherical chrome ball, or mirrored ball, basically. And what it can do is represent nearly all directions of reflection around an object. Around an object. I'm turning myself into tongue twisters. I just did another one by talking about reflections. Anyway, the trick is that every point on this texture represents a different direction that the vision can be reflected off. So everything except for the point behind the ball is reflected off this in some way. And we sample this by doing like a mathematical inversion of the reflection angle back to UV coordinates. So you think about it, a reflection of 0 degrees, I would call it, because if my reflected vector is going the same angle as my viewer direction vector, then they're both in the same direction. That is going to give me the point in the center. And then I'm going to be able to sample further outwards towards the radius of the circle as the angle increases. I'm not doing the maths here. The maths is complicated enough that it would take me a little while to do it, and this is like a diversion topic. It's not something that I'm really focusing on. But if you want to, you can have a look at the normals. So this is, someone has done just a normal map of which direction the normals would be pointing in, and then colored it like a normal map. Remember when we did normal maps, I showed you like this particular color where the I actually don't think this is blue pointing straight towards me or not, but anyway, it's sort of greenish going up, red to the right, and I guess blue to the... Or maybe it is blue towards me, and this is like a darker blue because it's going away from the other two axes. Yeah, so this would be blue with no red or green, yeah. So in the middle, it's kind of a mix of all three. Anyway, so this is an image showing all the normals pointing off in different directions. While I'm here, I picked this up from this website called Shader Toy. You may want to check it out. It's very, very cool. I'll click on it. Shader Toy allows you to render, and we're actually showing the frames per second that's happening here, allows you to render an object, or not just an object, but just a screen using a shader. So this is actually, you know, you can see here out vec 4 frag color, in vec 2 frag coordinates. So this is actually a fragment shader. And then it's got some code in here, which is just doing the calculation of the circle and creating the vec 3n, which is the normal, which is the, what is it, square root 1 minus the, I think this is actually the maths. This is the final result of the maths to figure out at which position, which vector. Oh no, this is the normal of this. So it's creating the normal based on the point, and we invert this maths to create to sample from this texture using the normals. So yeah, there's a lot of stuff on Shader Toy. It might be interesting for people to look at if you want to. It's amazing what people can do with just shaders. So anyway, that's weird how that is now not in full screen. Okay. So if we want to make a sphere map, we can take a photo using a spherical mirror, or we can do the same kind of thing we were doing previously to create a cube map, but this time instead of writing to multiple textures at once, we're going to write to different sections of this texture with multiple renders. We can kind of get away with doing less renders at this point. We maybe wouldn't do a render directly behind the sphere map because we can't see directly behind the sphere anyway, but even then we can see mostly behind the sphere, so we still might need 6 renders, and we just map them to different positions on this this sphere map instead of 6 different, you know, square textures otherwise. So I didn't mean to bash on sphere maps, but when I did the analysis of them, I figured out why we're not using them. So I had never really done a really clear analysis of what the difference is and why we would use cube maps over sphere maps. I've just realized that we tend to use cube maps over sphere maps, and then been teaching about that. So the pro of sphere maps that I could figure out is that it fits on one texture, which is a nice thing. If every cube map that we're using is taking up 6 textures, and it depends on the resolution of those textures. That's a costly technique, I guess, a memory costly technique. I might not be having this kind of conversation about like really saying there's so much weight against sphere maps if we didn't have this weird arms race that has happened with the GPU manufacturers, where one of the only numbers you can measure on the GPU for the quality of the GPU is the amount of memory on it. We have so much more memory on our GPUs that we can actually feasibly use nowadays. I mean, like the high-end GPUs might be able to use it, but the low-end GPUs, if you have a low-end GPU with a very large amount of memory in it, all you can do is store gigantic frame buffers that you don't actually have the processing capability to process in a meaningful way. So it's quite funny. So the sphere map is solving a problem that we don't have, a problem of running out of video memory. So it's quite funny. Anyway, so yes, if it's on one texture, that's a nice thing. But the downside is like, I get a little bit like, don't like wasting memory. It actually doesn't use all the texture memory assigned to it. So I cannot assign a circular amount of texture memory. I have to assign it, you know, in a rectangular shape for 2-dimensional use of memory. It has to be like this 2D array of memory. And so there's always going to be pixels here that won't be used. So we're in a sense, assigning video memory that we're never using. And it's funny that I say that's a downside of this, is that it's not using lots of memory, when I said that memory is not even a problem, but it's still a downside, right? The other thing that causes problems with sphere maps is how much detail they lose. You don't get a clear idea of what is here. So around the outside of this ring, everywhere basically around the outside of this ring, it's really hard to tell what the objects actually are that we're looking at. Because if you look at this row of lights, at some point it just turns into a smear across the surface, and it's really hard to tell that, say, this bit of it here or this bit of it here just used to be a circular object. I mean, even just here, the lights no longer have gaps in between them. Whereas I think, I don't know for certain, but I would assume that this row of lights here is a row of, like, is that windows in the ceiling? I can't remember exactly where this is, but I think this is in a cathedral somewhere or something like that. I assume this is a uniform series of lights, but the last 2 that we can see here are just joined together into this blob of light. So we're actually losing detail as we're going to the edges of it. The other thing is it's very viewpoint dependent. So if I was to make a reflection cube map of a particular object, and I wanted to make myself more efficient, I could make the cube map of that object and then not have to remake that cube map, especially if I can't see my character. If I'm just a floating virtual camera, I would never have to remake that cube map if the object never moved. I could just move around it and it'd be fine. But if I want to move around something that has a sphere map, I'm going to reach that dead spot very easily. I don't have to move very far until I can see the kind of dead spot directly behind the sphere map that it can't see, so I'd have to regenerate it more often. Another weird thing about sphere maps is that linear interpolation doesn't work properly on them. So if I am rendering from the sphere map's texture onto onto fragments, and I'm not necessarily calculating a new normal at each fragment. So I've tried to make it a little bit more efficient by just calculating the normals for a triangle, say one's here, and one's here, and I linearly interpolate between them on this texture to map the texture onto the object. I mean, that's something that we could do. I should have talked about that in optimization of cube mapping, but at the same time, it didn't make that much difference. I think the optimization issues with cube mapping is the number of renders, not the sampling of the texture. But the problem is, if I want to go between 2 points on a cube map, like say here and here, I should not be linearly interpolating across this surface. I should actually be drawing an arc around that surface, because that's the way that we should sample this if it's circular. So one of the, I guess, like, these are a lot of the issues, and so what I've accidentally done is like shown you sphere maps and said we're never going to use them, because I think that's the issue is, like, most of these issues here are actually solved by cube maps. So cube maps are going to use all the texture memory. They're also not going to lose detail at different angles. You're going to get a roughly even spread of texels to fragments, in a sense, no matter which direction you're looking at a cube map. It gets a little bit less dense closer to the axes, and a little bit more dense as you poke into those corners and there's more texels there. But it's not nearly as bad as the sphere map, where you genuinely lose detail. The sampling's a tiny bit more involved. It's not hugely more involved, but there's a bit more maths. Sampling from a cube map is just a linear interpolation, so it's very, very quick compared to sampling from the sphere map, which does involve, I think, I can't remember whether it has, you're forced in one way or the other. You're either doing a square root or a I think it's an inverse arctangent. So either one of those things is a little bit more expensive than a linear interpolation. I don't think that's the big deal, though. I don't think that's the reason you wouldn't use them. I think the biggest reason you don't use them is actually the loss of detail, which you get away with if it's a very small reflection, but the more important the reflection is, the bigger the problem that's going to be. So I think sphere maps have got just a little bit too much stacked against them for them to be something we definitely use. And Matt's saying sphere maps used to be more common, yeah, on older hardware. Because it doesn't need any specific GPU support, whereas the cube maps are actually built in. There's hardware that helps us with cube maps. Right, and the Metal Mario we're talking about was actually a sphere map. I mean, it makes sense that Metal Mario was something simple like a sphere map, because it just didn't have that much going on. And also, the Nintendo 64, just, like, compared to what we have nowadays, it's not a big, grunty, processing machine or anything like that. Okay, let's go on to planar reflections. So, planar reflections are, I say here the example, mirrors and water. It's not just water, like, there's lots of ways to do water that aren't planar, but water tends to form a plane on its surface, and mirrors generally are flat, but not always, but generally are mirrors that we're going to see a design so that we can see a view of ourselves, that kind of thing. So we have already covered arbitrary reflections in many directions. So the cube maps that we're talking about before, that can reflect off an object that sits in our scene. And if we want to, we could just use that. So if we want to, we could just build a cube map, put our mirror in the middle of it, no matter where it is, bounce our vision off that mirror, sample the cube map, and we'd be fine. It would work. The downside to this is the cube map is potentially only using, best case scenario, the plane that we're reflecting off is small. It's a mirror somewhere, and it only uses, say, 1 or 2 of the sides of the cube map. At most, you could still be in a bad situation and need to use 5 faces of the cube map, but there's a chance that there's always an expectation that a flat reflection doesn't need that many extra renders. So if we're trying to reduce the time complexity of what we're doing, to do reflections, and it can be a lot easier for us to use a specific technique for reflections of flat surfaces than doing a full cube map. Yeah. Matt saying, suspecting that Need for Speed Most Wanted was using this planar reflection technique. I think so. I'm not sure. I haven't looked into it, but the size of the size of the surface on the road makes me think maybe not, but potentially, yeah. So what is the answer to doing reflections of flat surfaces? Ray tracing. This is turning into a meme, but we're gonna roll with it because I've actually put it in several places in this lecture today. So yes, I do agree that ray tracing is the solution, in a sense, to reflections, and in some cases, yes, it's definitely being used. I realized I forgot today that maybe I should have installed a newer game rather than Portal. Portal is a very specific example, but Portal's more the technique we're actually going to use. But it would have been interesting to install one of the showcase games for real-time reflections. I think Cyberpunk and Control are the two games I can think of that were being showed off as examples for that. Jason, ray tracing, it just works. It just works. I forgot the guy's name. He says it all the time. I've seen the video of him saying it just works. The NVIDIA, I don't know if he's like the one of the company reps that talks at the conferences, or is the CEO. Todd Howard, there we go. Yes. Anyway, we're not gonna go too deep into that because ray tracing doesn't just work. Ray tracing requires, a specific model of graphics card and a whole lot of grunt to make it work. But anyway, so yes, there are some cases where real-time ray tracing for reflections is being used. But the fact that I could just name the games that it's being used in means it's not being used in so many others that are currently kind of on the market. So what we need to look at is what's actually being used in more games than a ray tracing technique. What are we doing when we don't have that computational power? What are we doing when we're at a RTX series of graphics cards, for example? Or what do we do when we simply are using the big grunt of our graphics card to do something else, and we want to do our reflections in a cheaper way? Oh wait, no, Todd Howard is, yeah, you're right. Todd Howard is CEO of Bethesda. It's Jensen. Okay, I'll look it up later. It's not super important. I think it's more of a joke than anything else. Okay, so let's go back to the tricks, because I think this is quite important when we think about this. Let's think about how we tricked people into believing there was a mirror in a scene, because that's going to give us some clues about how we might want to do it. So, the Duke Nukem example, in case you weren't there on Monday or haven't watched that one yet. Instead of genuinely reflecting off that surface, what they did in Duke Nukem was literally build the world again on the other side of the mirror. They made sure that, say, with this kind of desk here, because they couldn't be bothered building they couldn't be bothered rendering a sink or anything here. They just put a wooden block in your way. It has drawers actually, but there's no sink on the top, which is kind of funny. And they made it like this so you couldn't climb through the mirror, because the mirror is just empty space, and on the other side of it is a copy of the room you're in, a reflected copy of the room that you're in, and a doppelganger of your character model. Well, not a doppelganger, that's the only character model, because you don't actually have one where you're standing. But there's one there, and it's just copying your movements. So when you move, it moves, and they can do that in the frame calculation, right? So that's an interesting idea. We're not necessarily going to use that idea. We are not going to double up on the geometry, but we've got vector maths now. I mean, they had vector maths there, but they didn't necessarily have, in that era, a massive dedicated processor that was specialized in fast calculation of vector maths, which is exactly what our GPU is. So we do have that now. So we have vector maths, but we also have frame buffers and render targets. So what we could do is use some of these tricks to reflect our viewpoint. So we're going to go with the same idea that looking into the mirror should look back into the scene somewhere, and it should have the same kind of perspective that we have on the mirror. So we're going to talk about that and how that works. I'm going to build up our example from simple, I guess, intuitive ideas of how we do this into slightly more complicated, and looking at any of the issues that I've created from sort of coming up with this technique. So let's think about frame buffers and render targets. So we've used these to make cube maps. This is obviously not the first time I've talked about frame buffers. But let's think about our mirror there, or a plane that we're reflecting off, like the ground in the Need for Speed game that I was playing the other day. We can take that plane's surface, so the mirror's surface, and we could use that as the frame buffer. And what we could do is basically put a camera on the mirror. Just put it like in the middle of the mirror, for example, and say our main camera is looking in the mirror on a certain angle, and it should reflect off that mirror. We can use the surface normal of the mirror, and it should reflect off at a different angle. Let's aim the other camera in that direction, and then we'll do another render of the world from the mirror's perspective. So instead of copying all of the geometry and redoing all the geometry, which is pretty bad, that would double our double the number of triangles we have in the scene. We don't necessarily want to do that. Actually, no, that's not a good argument to make, because we're doing a second render, so we are effectively doubling the amount of time it takes to render anyway. But we're not necessarily copying all the geometry, so we're not using all of that memory to do it again. So we do a second render from the mirror's perspective. We take that texture that is created from that render, flip it, place it on the mirror, and then do a render from the scene, seeing the mirror. And what we should get is the image in the mirror should roughly be the view that we would see looking through the mirror, because it's our view bounced off the mirror, and the camera in the mirror captures the view in the other direction. The only reason this is going to work is that most of all of the normals of reflection are the same on the mirror. So we're gonna look at the mirror, and many different fragments are gonna look at the mirror, and they're all gonna bounce off in roughly the same direction. So we can take one camera view from that direction and assume that its sampling is reasonably similar to the reflected fragments, in a sense. So this is the setup. I think I've actually just spoken about this entirely. There's a bit of technicality here that we can talk about though, right? So we could place the camera at the center of the mirror. And this is where you can already see, if I am placing the camera at the center of the mirror, I am limiting myself to a certain size of reflection. The bigger it gets, the less accurate it's going to be around the edges. So the mirror's texture is the render target, and the camera just renders to that a frame buffer. So to sync up the camera with the main camera, I don't know, today I'm tripping on my own tongue a lot. To sync up the camera with the main character, main camera, which could be your character, which is why I'm slipping there. Anyway, we can replicate the up vectors, and the look at vector is reflected based on the surface normal for the mirror. I don't have to tell you what the third axis is of the camera, because as we know, once we've got two vectors to make an orthogonal basis for that, I can just cross product those two to get my third vector, which is the sideways vector. I think it's the right vector, upper right and look at, yeah. Which would make it a left hand, yeah. Anyway, we can then render the scene from the mirror camera, and then that render from the mirror camera is saved in a frame buffer that becomes the texture that is used on that mirror when the main camera renders. So what we'd basically be doing is we'd be rendering first from the from the mirror's perspective, and then second from the main camera's perspective. So this is one. Here's a diagram of it. I wanted to make sure I spoke about it before I showed this diagram. Okay, so main camera viewing this mirror. So there's a mirror on a wall here, and the view bounces off that onto this orange vector, and then we create the camera that's looking down that vector. And I drew some objects here just to make it obvious that there are objects there, and the mirror's camera is going to render those objects to look like this. We would then use this texture on the mirror. That texture would be flipped onto the mirror, because from the viewpoint we'd actually have to flip it on the horizontal axis here. If you kind of look at where where you'd expect the vision rays to bounce off, you can see that this needs to be flipped for these objects to appear at the same kind of orientation that they are now. Okay, so this looks like it, right? We've completely solved the problem. There's no issues that can possibly arise from this setup like this. We're fine. We're good to move on, right? Obviously not, if I'm going to say that. Let's pick at this and see where there might be some issues. Funny thing about this technique that I'm showing here is very, very close to what was in Portal 1. It was just a camera sitting on the other portal, and it's effective enough. You know, we're actually going to believe this most of the time. So a little bit of analysis of this simple mirror camera that we've got here. It is roughly correct. The vision angle is roughly correct. We are going to be able to do a frame buffer, a render texture. And we've also got a kind of a bonus in that we know that the mirror is never going to be as big as the entire scene, or depending on how much detail we want to do on this, we can expect that it's not always going to fill the entire screen, so we could do that mirror render at a lower resolution. So if we're doing it at a lower resolution, we're calculating less fragments, we're going to save a bit of time. The second render that we're doing for the camera is much faster than 6 renders for a cube map, right? So we've meant that if we use flat mirrors and not the full cube map, the cost to our overall time to render is much lower than it is for the arbitrary reflective object like the car that needs multiple renders to make its cube map. So there's a couple of nice benefits to using a completely different technique for planar reflections than it is for arbitrary reflections, cube mapped reflections. But the cons, again, how many mirrors do you have? If we're putting a camera in every mirror, then how many mirrors do you have? Because it's going to be an extra render for each one of these. Worst case scenario, these are looking at each other, and then you have to decide which one goes first. Or you want to be really full on about this, and you get recursive on it, and then you have your infinite mirror with 2 mirrors on either side of each other, and things are going to get a little bit fiddly like that. There are some issues though. So there are issues with the camera location and then the near plane of that render. So depending on where the camera is, its frustum is looking into the world from the mirror's position. Where is its near plane? What's the angle of its near plane? And is that causing any issues? I'm going to go into this and talk about it in a second, actually. And also, is the perspective from that camera correct? So we are looking at the mirror from a certain distance, and then the mirror is rendering from exactly where it is. Is that causing a problem or not? And it might well be, depending on how we've implemented what we're doing. So I say that this is probably going to work, and it has worked. So there's plenty of games out there that will go as far as I've said here, and that's it. That's enough, because the mirror's not a vital part of the scene. It's not the super important part of the scene. It's just there. You can just kind of see it working and go, yep, that's enough. I'm okay with this. I accept that that's a mirror, because as I'm walking past it, I can see the view in it, the perspective of the view in it changing by the opposite of the direction I'm walking in. So I'm just like, sweet, it's a mirror. It's fine. I'm not going to judge it. But if I was to get up really close to that mirror and look at the angles of things as I'm getting closer to it and seeing it, I might start to see issues in it. So let's have a look at some of those and some of the pitfalls that we might have from using a camera that's just kind of stuck to the wall. Like, we could nearly say that the model that I have presented you for reflection here is not reflection. It's a webcam and a monitor. So there's a camera and a monitor on the wall, and the camera is set to look at where your eyes are and then reflect and then angle its view based on where your eyes are. So what we're getting is the view from that camera, not your reflected view off that monitor now, as opposed to the mirror. So if we're getting that, we're going to get some potential issues, as the camera can and can't see certain things. So where is the near plane of this camera? Is it too far away from the mirror? Is it on an angle from the mirror? So this near plane here, so I've just drawn this dotted line in this camera to show its near plane. This is an exaggeration. Near plane's usually much closer to the camera, but I needed to draw it so you can see it. And you can see that here's my mirror, here's my near plane, and here's a gap. So everything in this section here won't appear. And even if we want to make this near plane really close to the mirror, it doesn't matter, because if this camera is on an angle, its near plane is perpendicular to the camera's looking vector, right? And that is not always the mirror. So the mirror's here and the near plane moves around, tilts up and down, depending on which way we're looking at the mirror. So if it's going to do that, then we can get issues where the near plane can cut off things that are close to the mirror. And one of the things that we want most, I think, is for the objects really close to the mirror to definitely appear in the mirror to give it that look of reflectivity. So we're going to need to do something with this near plane. And the other option for this near plane is what if we push it as far back as we can to get to not miss objects that are close to the mirror. And when we do that, we risk the near plane actually being behind the mirror. And this might be okay. It might be okay if the mirror and the wall there don't have any other geometry. But what if that wall is just a wall in a building and there's actually another room behind it? We clip far back enough with our near plane and we're going to render whatever's behind the mirror instead of the mirror itself. Instead of the objects that are sort of in this room. We could actually render the objects in the room behind. So this is definitely something we have to deal with. Where we're going to have an issue of exactly what is and isn't visible based on the fact that our near plane is never, well, not never, you can have a perfect reflection and have your near plane exactly parallel to the mirror. But the odds of that happening are so low that we really need to deal with all of the possibilities of this near plane being somewhere else. So what we can do with that is we can either modify the near plane or create a culling plane. Actually, I think it might be called a clipping plane, not a culling plane. So if we want to, what we do is we just, let's just push the camera back. Push the camera back a bit and we say, okay, our near plane is no longer going to be parallel to our look vector. So it's not going to be a plane parallel to our look vector. Instead, it's going to be a plane that arbitrarily always matches the mirror itself. So we can do that in a couple of different ways. One is culling. So we have our near plane and we put our near plane in its kind of normal position, very, very close to the camera. And then we make a custom clipping plane that is in the mirror itself. And what we do is we say everything that's closer to the camera than this particular plane will not be rendered, and everything that's in the frustum otherwise will be rendered. So that's a nice way that we're going to do that. It's basically just looking at the distance to the objects calculated against this plane and saying, okay, we're going to not render any objects that appear in this section, and we're going to render everything that appears in this section. You can also do this purely in maths. You can actually modify the projection matrix for this camera, and in modifying the projection matrix, you can make the frustum actually change shape. So the back of the frustum, the near plane of the frustum, is actually aligned with the mirror. You can do this just with the mirror's world coordinates, and you do it by modifying your model view projection transform that we made a few weeks ago. A few weeks ago? Months ago now? I was just thinking like how far we've come now that we're in week 9. You got to be a little bit careful with that because the modification of the projection matrix doesn't just modify the near plane, it's going to modify the far plane as well. It's going to do really weird things with the far plane because if we tip the near plane, the far plane's kind of, it's not exactly going to go parallel, but it's going to go into this weird shape. So if your far plane is so far away that you don't mind, if you know that your far plane kind of extends beyond the scene, you could get away with this just purely mathematical shifting of the frustum to fit the mirror. But I think the easier way, which I think is more costly and computationally, but easier to just think about, is just put a custom. I can't remember whether it's a culling plane or a clipping plane, because it could be a culling plane that clips out certain geometry that's too close to it. Yeah, but it's probably one of those interchangeable titles. Yeah. So that might give us that kind of correction there. So what we can do is like, okay, that's fine. It is a clipping plane, isn't it, Matt? Yeah, I thought so. It's weird because I wrote it. I reckon what I did was like I was thinking a clipping plane that culls things, and then I wrote culling plane there. But just reading that a couple of times as I was talking about it just didn't look right to me. So yeah, I'm going to change that to clipping plane. Yeah, so if we do that, we can now get rid of the problem that our secondary camera here, our reflection rendering camera, is now rendering things exactly from the front surface of the mirror forwards. So this is getting rid of the issues of like things magically disappearing when they're in the reflection, or worse, the back of the wall of the reflection appearing. So if we put that in there, that's probably going to help us. We do have other issues though. So I can ask, under scrutiny, does this mirror look like it has the correct perspective? Excuse my not quite straight lines here, but you get the idea of what's going on here. So the camera in the mirror has its frustum, especially if I'm just doing a minor shift of the camera, just pushing it back from the mirror a little bit, you can already see here that the frustum that the camera's viewing doesn't include objects that are on this side or this side that are right in front of the mirror. They're right there in front of the mirror, right? So the problem is that if I'm looking from here, actually let's go to this one. If I'm looking for here, and I look at the edge of the mirror and bounce it off, and the edge of the mirror and bounce it off there, I'm not necessarily seeing anything from this camera. Because this camera, if it's right here, like just behind the mirror, looking forward, it's like looking from a section in the center of the mirror. It's not looking, it doesn't have its viewpoint as the entire width of the mirror. So I can actually be missing things there, and not just missing things, but as things get further away and I can see them, they're in a slightly different perspective from the perspective that I should have looking in the mirror. So their frustums not being equal here is causing them problems. So how are we going to correct this issue? And yes, the answer isn't ray tracing this time. It's actually completely not ray tracing, unless we replace the entire thing with ray tracing. But no, what we want to do is try to get the mirror's camera frustum matched up exactly with the reflected frustum here. So the reflected frustum isn't just the lines that are lined up with the edges of the mirror, because this frustum actually is much bigger. It's looking at the mirror and the rest of the scene, but we still want to make sure that the particular angle of how our vision meets the mirror is matched in the camera that's rendering it. So one thing that we can do to do this, which actually works quite well, is what we're going to do is just upgrade our reflection. So previously, I said what we're going to do is just mount a camera at the mirror, and what we're going to do there is reflect the angle of view. If we reflect the angle of view, then we can see from the camera's perspective, and we'll get a reasonably good reflection. But what we're seeing is that causes a problem where we don't see the same things. So we can leave gaps depending on how big the mirror is, and our perspective is not the same because the frustum's not the same. So there'll be objects that are obscured in this camera's view that this camera can see, just because of the perspective shift between different things. So it does look a little bit weird. So what we do instead of just reflecting the angle of view is we're going to reflect the angle of view, but we're also going to reflect the camera position. So we're going to take this secondary camera and we're going to say, all right, we're going to be the same distance away from the mirror on the other side that this camera is. And this is going to get us a much better look, right? Because when you think about it, when I'm looking into a mirror from a certain distance, hey, there's mirrors behind me, that's great. I'm looking into that mirror from this distance. If I get closer to that mirror, I should see different things. The closer I get to that mirror, the wider my view in that mirror can possibly be. The further away I get from that mirror, the more I'm looking through just a tiny little section, and I'm going to see just a tiny little reflection or something. So, if we have our virtual camera, and we just move it based on where this camera is, and then we take our render from that camera, we're going to get a much more accurate one. So, we're not just reflecting angle, we're now reflecting position also. And the nice thing about this is the risk that we had previously was this camera was going to go so far away that it was going to see a big chunk of the scene behind it, behind the mirror, and then render all of that and make stuff appear in a bad way. So we don't want that. So we've already solved that with our clipping plane to make sure that everything behind the mirror wasn't being rendered. So we make sure that we're definitely seeing the stuff that's in front of the scene. So we're not accidentally getting objects in the other room behind, for example, obscuring what the mirror should see. So with that, we've got a decent outcome, you know. We now have a camera that can render from the mirror's perspective, and we have a reasonably good guarantee that A, it's not going to accidentally render something behind it, it's not going to miss the objects that are close to it, and it's also going to see the view from a realistic viewpoint based on our position in the world. So that's a decent solution. That's probably going to do what we need to do. But the question now is like, do we actually even need this camera? So I've put together an idea, and looked at some of the issues it has, looked at some of the reasons why it might not work, and then added upgrades to this techniques, so it probably works. And so we're at this point. But the question is, could we have done this in one render pass? Can we do this reflection without the extra camera? Can we do it in a single pass? So instead of reflecting using a camera to reflect our view into the world, why don't we just reflect the entire world? So there's a little quote there for those of you who are fans of the Matrix. What if instead of reflecting the viewpoint, we lean in to the Duke Nukem strategy and we reflect the entire world? So what if in our render of this camera, so these are the same objects that we had. I should put a camera in here. If my camera is viewing at this angle, what it would see is these objects here. So what I do is I just take a transform, and it's a pretty simple transformation matrix where what I do is I take this plane in my scene, and I take everything in my scene and I reflect it across that plane. So I take the position of this object, and there's a vector here to the plane, which is a certain length, and I can take double that vector onto the other side of the plane, and I can place that object there. I can also scale that object by -1 in that direction, and that will flip the object around in a sense. Hamish is like, this is full circle, we're back to just copying the scene. But this isn't necessarily a copy of the scene, because we don't need to double our memory for all these triangles. We're just going to use the same triangles, same scene graph, same geometry and things, and just move them to the other side long enough to do a render and then put them back again afterwards. Or even move them so that they appear in both of those positions at the same time during our render. So we're accessing the same vertex buffers and index buffers and things like that, but saying, okay, do this render with this thing as if it's in both positions at once. So this is like starting to think this is potentially viable, right? Because we've just got a single render pass now. So if we're going to do this with a single render pass, with these objects kind of ghosting, they're doubling up like this, there's a possibility here. And you might be thinking, Mark, why didn't you just do this first? Why did you teach us this other technique with this camera and stuff like that? I'm about to show you why this doesn't work. All right. So, what are the pros and cons of this? And this should remind you of like the pros and cons of the sphere map is that there's only one pro, and everything else is stacked against this idea. So the pro is this is a single render pass. We don't have to do two phases. One phase where we render from the reflections perspective, and another phase where we render from the main camera. I don't know if you can hear that coming through the microphone, but it is raining very, very seriously right now here in Sydney. I did get a warning about this yesterday. A friend of mine was saying that we've got a severe storm warnings in Sydney at the moment. Hopefully everyone's okay out there. I mean, it's a good time to just stay home and watch your graphics lecture instead. Anyway, what are the downsides of this technique? What are the downsides of me saying, oh, let's just reflect the entire world instead of just reflecting the viewpoint in the mirror? So what's happening with our lights? Are our lights reflecting also? So if I take all of the lights from one side of the scene and put them in the other side of the scene, and then calculate as if they all exist, those lights, I've doubled my point lights, and the point lights are now pointing at those objects from through the mirror, but not necessarily through this specific window that the mirror would reflect light, but they're just everywhere in the scene. So we've accidentally doubled our light, and we're potentially spilling light into the main scene from these reflected light positions, or vice versa, spilling light into the reflected scene from our main scene's positions. And so you could say, why don't we just don't reflect the lights? If we don't reflect the lights, then there's no light in the reflected scene, right? Yeah. Yeah, Matt's saying there are ways to do this. Like there's ways that we can work around this idea. But and there's other issues, like are our directional lights still in the same direction? And this is something that I think Hamish asks there as well. What happens if there's a room behind the mirror? Yes, if there's a room behind the mirror, did we just reflect objects into our real world from the other side of that plane? So that's a possibility as well. We would have to actually analyze which objects are in the real world versus which objects are behind the mirror. So we can do that. I mean, I just said we were adding a clipping plane to the second camera render. So we could potentially do that, but we do have an issue that we would have to do that, right? So we have this idea that we could reflect objects into the scene by accident. And the other thing is we're going to reflect a whole bunch of objects that aren't even relevant, or visible. So sometimes it's easier, instead of writing all of the code to make this work here, like as Matt's saying, there are workarounds. This is entirely possible, which is why I'm talking about it. It's possible and it's plausible to do this. However, the amount of work necessary to do this extra render from this other camera's angle, what we do is when we're just leaning in on the fact that all the technology that we've built for rendering from a camera already exists. So if we just reuse the technology that already exists for this thing calculating its frustum, this thing deciding what is and isn't visible, this thing doing all of its culling of objects that aren't in the frustum and stuff like that has already happened. We don't have to do as much extra work for this technique as for this one. This does exist though. I couldn't find specifically which games used this kind of mathematical reflection technique, but it definitely exists, and other people have gone through and actually done all the maths on this and verified that, because you think about this, reflecting an object onto the other side of a plane, that's not mathematically difficult. Like, I think if I left any of you with enough time, you'd be able to figure out the transformation matrix that would do this. But there's enough fiddly stuff that you have to do here in order to change the behavior, in a sense, of your renderer to make sure that your lights are working and stuff like that, and that you're deciding which things are going to move onto the other side of the mirror. It's enough that we can get away with just doing it from the other camera. Matt's got some more details there as well. So if you're hiding a room behind the mirror, you can draw the mirror scene, then an invisible window quad to the depth buffer, then the normal scene. Anything behind the mirror fails the depth test. That's kind of cool. Yeah. So there are techniques to make that work. You can make it so that everything on at a particular depth from the mirror is, I think at that point, too close to the mirror because they're kind of behind the mirror to actually appear. So there's tricks to make that work. But I'm pretty sure, actually don't know, because it's actually hard to find the algorithms behind what people are doing in games. But I'm pretty sure that the extra camera is something that happens more often than the mathematical calculation, but I'm not 100% on that. Okay. So another option that we're getting here is the rippling lake. So you've probably seen this kind of thing before, where a surface is not perfectly flat, so imperfectly created glass, or what's more interesting is someone throws a pebble into a lake and you see all these ripples come out of it, and you see the reflection from that. So how would we do planar reflections where the geometry of the reflective surface might be a plane, but its normal map is not flat, so its normal map has ripples in it or something like that? And the answer is ray tracing again. I'm joking, but yes, it is actually. If we're directly reflecting our view off many different parts of a plane and it has a normal map, then we would be sampling from that normal map and we would be getting different directions off it, and we could definitely do that. I didn't actually put this in the slides because I didn't think I had time to talk about it today. Yeah, Matt's saying that in like at a certain era of game machines where video memory was at a premium, the single render mirroring was something that happened more of, especially when you've got really simple geometry. You can flip that geometry quite easily. Anyway, so I didn't talk about it, but there's actually another technique that they call ray casting rather than ray tracing, where it's like ray tracing with less bounces, in a sense, where what you could do is for every fragment in the scene, you would bounce off the mirror and you'd hit one object, and that would be enough. And you could do that instead of ray tracing, where you need to bounce off that other object and then find some illumination for it and that kind of thing. That's something that can work. And a lot of really simple ray tracing models are just gonna bounce off the mirror, hit something in the scene, and say, what is the illuminated color of that thing in the scene? But we can do simpler techniques than that. So the rippling lake we can do with some fudgy maths. I'm going to call it fudgy maths because it's not real maths. We're going to do like an approximation to offset our sampling. So what I mean by that, by offsetting our sampling, is to say that we can generate the reflection texture in the same way that we were doing before. So we could say, place the camera below the lake at the same distance that we're above the lake, use our clipping plane and do our render, right? So we've got our view there and then our render comes out from above. And then instead of just slapping that texture onto the lake, so doing that exact perfect mirror, what we can do is when we sample from the texture, the first thing we're going to sample from is the normals. So in our fragment shader, looking at that texture, we're going to sample the normals, and all the normals are going to be tilted some way or the other. If it's aiming straight up, then we would just use the texel that we can get from our texture coordinates there. But if it's not aiming straight up, we can just move the texel that we sample to somewhere else on the texture surface. And I'm not even going to talk about the maths for that, because we could just think about the XY components of the normal and take that, but that's not going to be correct. But we're talking about an approximation here. It's just not going to be correct no matter what. And the more correct we try to make it, the closer we're going to get to actually just calculating the whole thing. So this is about doing this in a quicker way that gets away with looking mostly correct without needing to be 100% correct. So we can take the normals and say we're just going to offset where we're sampling based on the angle of the normal. The only thing we need to be careful of here is sampling outside of the 0 to 1 for the texture. So around the edges of this rendered texture, if we go off the edge, we're potentially going to have some issues. And that's where we change our sampling style for our textures to I don't know, maybe clamping on the borders or something, so it's just always the same color if we go too far over. Generally, if we've got ripples on a surface, we're not going to notice too much if they're not 100% accurate. What we're looking for is the indication that the ripples are happening rather than a genuine need for perfect reflection off these little ripples. Like, our brains aren't smart enough to tell exactly what a perfect reflection should be, and so it looks good enough to trick us, we're probably going to get away with it. So that's the kind of thing we might do if we've got a normal map on our reflective surface. You could even use this to do like your kind of funhouse mirrors and that kind of thing. But I think if I was going to do funhouse mirrors, like, you know, like those mirrors that make your head look really big and then your body really small because of the angle of the mirror, I'd be tempted to do an actual reflection for those. Because if you have a gimmicky mirror like that, you're probably going to want your player to actually really look at it and spend time with it, in which case you need to do you need to make sure your reflections are reasonably accurate. And this is not super accurate. This is just a guess that runs quickly. So, thinking about planar reflections and how they work, there's a reason why there's so few mirrors in games. So, up until recently, the second camera technique that I was talking about is something that was used, I guess, for the last decade or so. But it's starting to be replaced by ray tracing, but I think the interesting thing is, like, this question will have been asked in every game where an idea comes up that we should have a mirror, or we go into a real world environment and there happens to be a mirror there. And the question is always, is having that mirror in the scene worth halving our frame rate? It's not definitely going to halve our frame rate, but it's in that order of magnitude, right? If we have to do a second render from the mirror's perspective, then it's potentially going to halve our frame rate. So I would say that most games in the era, if we're talking late 1990s to 2010s, anything before the 1990s was just like, nope. Except for Duke Nukem. Duke Nukem was showing off the idea that they could render a mirror. But they were tricking us. They weren't technically rendering a mirror, they were just rendering extra scene. But either way, they got away with it, which is really cool. But anyway, in that period where the second camera technique was possible, it still wasn't used that much. I mean, look for mirrors in games. Look for genuinely reflective mirrors, and look how what could have been genuinely reflective objects in that era are not. They're just specular. So they'll have a nice specular map and a normal map, and they will reflect just lights, just white light, or the color of the light, but they won't reflect the scene. I think the classic example is Master Chief's helmet. So the Master Chief in Halo, this helmet, it's curved, and it is shiny gold, and it never shows the environment. It's never, well, as far as I've seen, it's never shown a genuine reflection of like a real-time cube map anywhere. Whereas the Need for Speed games are like, totally, let's go all in on this. Like, we want to really show off how good we can make these cars look. So they went for this, and it became a feature of those games. And now every driving game needs real-time reflections. Like, no one will accept a driving game where a car has a matte finish. And I think that's kind of cool. Like, you know, like your genre dictates whether this is worth it for you or not. Okay. So let's go on break. Ooh, I have used up a lot of time in the first half. Anyway, it's okay. I think we'll still have enough time for what I want to do in the second half. So, homework. I have not given you homework recently. I gave you homework at the very beginning of the course. Now I'm going to give you some more homework. So there's been a while. Two films, and this is the same team working on these two films under James Cameron. I think this is ILM, Industrial Light and Magic. 1989, The Abyss, liquid simulation in a film. Environment reflections needing to somehow do reflections also of people. And you can see they were not super successful in it. They're successful enough to be believable, but you watch it and you just go, oh, this is CG. I can see this is CG, right? And Terminator 2. The same thing going into liquid metal where it really does reflect a lot of the environment. There's a lot of shots taken of someone holding one of those chrome balls and walking through the scene where the characters were going to be so that the CG artists had a reference for what they were going to do. Half-Life 2 Lost Coast should not be surprising to you. The last few lectures when we were looking at HDR and stuff like that, I've definitely put pictures of this. I can't remember if it was the thumbnail or just in the slides. This was a tech demo by Valve, and they implemented HDR with Bloom in this. We're going to talk about Bloom today, actually. I decided to use Bloom as the post-processing example. And cube map reflections, and also refraction, which we didn't even talk about, is the idea of like using cube maps to do transparent objects and having the light turn as it goes through those objects. And another thing I thought might be interesting, this is about to be an example that is not very useful to us, which is the Grand Theft Auto series. They're about to remaster it, and when they remaster it, it's cool. It's great that it's getting remastered because it's like a very, very interesting game series. But if they remaster it, then our analysis of the graphics technology then kind of falls flat because all the older ones are going to get brought kind of up to spec in a sense. But if we go through now, if you want to, and you play the old ones, you will see the kind of incremental increase in graphics tech as we go through, and we get better and better at what is effectively the same game. I don't want to be too mean to Rockstar, but the same type of environments, the same type of situations happen in the different games, and how the identical, I guess, gameplay loop is there, but the technology with which to display these environments changes drastically over the 15 years, I want to say 16, looking at 16 years of this game's development. So I think it's really interesting. There's not many franchises that span enough time to be able to judge how things have changed over the years. We end a bit early because GTA 5 was so long ago, but I guess from 2013 onwards you could go on to look at Red Dead Redemption, but it's not the same thing. It's a different renderer. Well, I mean, it might be the same renderer, but it's being used in a different way. So, yeah. Anyway, let's go on break now. It is 11:18, so we'll come back at 11:23, and we'll start talking about post-processing. All right, see you soon. Alright, I'm back. Did I say 11:22 or 11:23? I know I specifically said the time, and it's going to be exactly 5-minute break. I think it was 11:23. Let me just fill time for a bit until 11:23 in case people are timing the break specifically, which I'm sure like some people are going to be. Well, I mean, I should be timing the break specifically at least. There's probably a lot. I haven't read a lot of it, but I'm sure there's probably a lot of research on human attention spans and exactly how long you should be doing things for. I have thought of teaching a course like this with less live lecture content and more like 15-minute videos. The way that you would learn something if you're watching on YouTube. And I think that actually matches the human attention span better. But what it takes away is the real-time event of the lecture. So if someone's going to sit down and watch a big thing in real time, like theater or a movie or something like that, then you do commit to your kind of 2 hours long thing. So I guess that's where a lecture sits nowadays. Or like if you're going to watch someone streaming, then you'll be there for hours and hours and you're totally chill, you can do that. But I think when people are streaming, you're not paying close attention and you don't have the density of detail that you might have in a lecture. Jason's saying GTA 5 graphics are really holding up. Yeah, I was surprised as well. That it's 2013, but it's feels kind of present. I think that that's because it's mid to late console generation. So that's the PS4 generation, and so it's pretty good for that era. And the next jump is, say, PS5 era games, and I think you'll probably be surprised with how good GTA 6 looks, I guess. I don't know if GTA 6 exists, but when it comes out on the PlayStation 5, I assume it will be another jump up. But we haven't seen very many games make that jump yet, because we're still seeing things that are sort of hybrid last gen, current gen consoles, and so they're being, in a sense, held back to the quality of GTA 5 because things were still made for the PlayStation 4 up until recently. But there should be a jump up. Every time a console generation moves up in its capability, the software then gets to utilize that capability, and then it jumps up. It's funny because advances in PC don't tend to make the same kind of changes because PC is like a curve. It's like a slower curve that goes, whereas the consoles is like a flat line that then jumps, and another flat line that jumps. So it's more obvious when console tech changes generations. Okay, cameras and portals, very, very quickly. Here's an example from the very game I was playing at the beginning, and I was talking about that at the beginning. The idea of using a camera and a render texture is not just for reflections. So the reflections are very, very constrained as to where the camera should be, so that we'll believe the reflection, and where the render texture is going to be, so that this is the mirror on the wall, that kind of thing. But we can actually place that virtual camera anywhere in our scene if we want to. We can orient it in real time in the same way that we're doing for a reflection, but we can render to a texture that's entirely somewhere else. So this is cool. This gives us the idea to put things like security cameras in games where I can have a tiny little render texture that's on a model of a computer monitor or something, or a monitor or a model of a TV on a wall or something like that in our game, and then have a different renderer somewhere else showing what's happening in real time. So you can use all those kinds of games where you're like spying on other things and stuff. You can use cameras and render textures for that. This example here is using portals. So the camera is off to my side there somewhere so it can see me. This is my little edit. As you can see, if you zoom in, you'll see the little edit there on this one. Did anyone notice the little edit that I did on the Need for Speed? I forgot to put that in the Discord. I'll throw it in the Discord later, see if people are noticed it. Okay, so that technique, not limited to mirrors. It's also much easier if it's not a mirror. You know, you don't have to match up the perspective. You don't have to match up the frustum or anything like that. If you go, no, this is just a camera looking at the world, right? So you can place it anywhere you want. So this is actually a much simpler form than the reflections. Okay, so let's go on to post-processing. We've got the idea of renders to textures and frame buffers, right? So I've shown you several different things you can do with rendering to a texture, but it has so much more. This technique of just simply rendering to a texture and then doing something with it, or rendering to a texture in a particular way and doing something with it before it ends up in the main frame buffer, there's heaps of stuff we can do. So I'm going to look at one particular form of this, which is post-processing and screen space effects. Largely the same thing. It's kind of like two different names for a similar technique, and the technical side of it's going to be reasonably similar. So we can render our scene to a frame buffer, not necessarily the frame buffer, because if we render to the main frame buffer, that's going to the monitor. Right, we can still edit stuff there though. Before we finish our fragment shader, we can still edit stuff. But what we can do is we can render to a different buffer. So we will make our own frame buffer exactly the same size as the screen. Well, it's not always. You can do what you want with it, right? But usually, if we want to retain quality, we make it the same size as the screen. And then what we're going to do is modify something in that buffer before we write it to the screen's buffer. So we call it post-processing because it happens after the render is technically finished. So the render from the camera's perspective is technically finished. And then what we do is we take the screen that's about to appear on the monitor and we modify it in some way. So really, really simple post-processing that we could do is we run the equivalent of a fragment shader on that texture. So we just look at each of those fragments and we say, all right, we're going to do something else with these fragments. And a really simple thing is to go, all right, the colors that are about to go to screen, let's modify the colors that are about to go to screen. There's actually heaps of stuff you can do by just going through all the pixels one at a time and changing their color in some way. So really, really simple thing is a black and white filter. This is something that you could do, and I think this is a really good exercise that I don't know if it's going to be black and white, but something like that I think maybe we'll have time for in the final tutorial. I can't remember what the plan was. I know I made the plan. Doesn't mean I can remember it. Next week is so far away right now. Anyway, so what we can do is we can render our scene to a temporary frame buffer. Then what we can do is we can read the RGB values one at a time, average out the RGB values. So what we're going to do is we're going to take the total amount of light in every pixel and then rewrite the average amount of light in every pixel to all the RGB values. So the R, G, and B are all going to be equal. And if they're all equal, then we're going to get a grayscale. And then what we're going to end up with is our scene, instead of having color, is going to go to black and white. I was going to put some images up of that, and I thought, I think people will figure that one out. I probably don't need pictures of black and white. I think people can handle that one. Right, so that's a really simple thing we can do with post-processing. We can take the colors in the scene and alter them. And if we alter them in the same way across the entire scene, it can drastically change the way the scene looks. So we can do things like a sepia filter over the entire scene to turn everything into shades of brown and stuff like that. And that's actually going to give it a particular feel, I could do something really cool if I want to. I could do like a Sin City theme where what I do is I make everything black and white, except if things are a particular shade of red, in which case I hypersaturate the red. So I boost the red and reduce the red and green. And then what I get is like a largely black and white world with these splashes of bright red in it. And I can do that from a color render into this effect. There are heaps of things that people do, and so there's other things we could do with this. So I've got some ideas here. These are not the only things that you could do, but post-processing has a very, very wide array of possibilities. So I could do a night vision mode. So I could green tint everything. Instead of turning everything black and white, I could turn everything into mostly green, and then change the curve so that there's this over-intensity at certain brightness levels, and at other levels it drops off dramatically to show that kind of like hyper contrast that would make it look like it's processed night vision, that kind of thing. I'm just making this up. I don't actually know what night vision genuinely looks like. I know what night vision mode looks like because of games, but I don't know if they were accurate in what they were doing or they just did what I'm talking about here. Right. We can do some weird magical opposite effect by inverting the colors. So basically we just take every color and we change its distance between 1 and 0 to the opposite, right? So you can get some interesting stuff like that. That will change the balance between red, green, and blue and make bright things dark and dark things bright. Interesting. Another thing I thought was like, let's do some blood rage effect. So what we can do is we don't just sample the colors from the pixels. I'm going to call them pixels because they are relating to the pixels that are going to be on screen. They're not pixels. They're actually just texels. They're texture coordinates. But they're kind of specific because it's a copy of what's going to go to screen. But what I can do is I can take the pixels near the corners and the edges and turn them red. And as I get closer to the center, so it doesn't obscure your vision entirely, I can take out that redness closer to the center, so you can still see things, but the entire kind of border of your screen goes like kind of transparent red, and I can use that to flash on and off and things like that. And then I could make an effect that happens when my character goes into a blood rage or something, you know, and it's quite believable. And this should be memorable because you've probably been in situations in games where you've seen something like that happen. We can mix effects together. So we can do something like a head-up display. I don't know how well you're going to be able to see this. This is Halo. I had to like limit the amount of times that I tell people stuff about Halo. It's like one of the franchises I like, because I could have, you know, said GTA through the years. I could say that about Halo. Halo, actually, you can do that in one game, the current Master Chief Collection. So that's a thing. I should stop just spruiking Halo at every opportunity, though. But people know that about me already. If I tell you to play Halo, that's just me at a default, normal level. So, HUDs are not always done with post-processing. A lot of the time we think about a head-up display, post-processing being done in like fragment shaders and stuff like that feels like an over-the-top way of doing things. But you can do some HUD elements definitely. In post-processing, because usually it's just a 2D element that's just written over the final frame. But if we were going to do something like a transparent HUD like this, we can definitely do it as a post-processing effect. So we have the HUD and it has some alpha and we blend them together along the way. Not always. Like, I mean, HUDs tend to be separate from our 3D render chain, but you can do things. So you could, if you wanted to, do really specific things where this HUD actually takes some effects from the world. The other thing we can do is we can blend pre-made effects with the screen. So here, this is from Borderlands. We have multiple things happening at the same time here. So I have an elemental lightning effect. You can see the lightning here, and there's a bit of it on this side as well, happening to my character at the moment. And so that is happening in screen space. It's an animated thing happening in only the screen space. It's not happening in the world, in a sense. And also here, these hexagons here, very much like, you know, that blood rage effect that I was talking about. But instead of it, this is a flashing, pulsing kind of thing where I'm taking damage from that side. So to tell your character that they're being hit from something that they can't see, they can get effects. You can make effects like this appear, and you can alpha blend them with whatever's in the render for the scene. So what we can do is render the whole scene and then add these effects on top of that, blend them together, changing the color of the individual pixels based on this other texture that's been created, this other semi-transparent texture, and then render that. And you can see how the HUD elements are kind of different from that, because regardless of what's happening with this effect here and these effects, the actual kind of functional HUD that's here is just being overlaid over the top. It's completely covered. Although part of that's actually transparent, so I guess there's other stuff going on there. But I mean, alpha blending two things together is not super difficult. So this is a lot of stuff you can do, and all we've done here is said we process the scene, and then we have some methods to change the color of the pixels in the scene before we send it to the mainframe buffer, and then send it on its way to go out to the monitor. So lots of interesting stuff that we can do there, but we're not done. There's a lot more we can do with post-processing. So we can use these things we call kernels. A kernel here is a mathematical concept, the idea that in a matrix, we can have single cells of the matrix be influenced by other cells. So it could be in this situation that there is some data in this pixel here that is built up from the data of the pixels all around it. And the beauty of being able to do this in the in post-processing is it's actually impossible in the fragment shader, because if we tried to do this in the fragment shader, so we render a fragment and we say, hey, look at the fragments around you, and use their values, their RGB values, to do something to your RGB value. There's no guarantee in any way that when you're rendering a fragment that, say, for example, the 8 fragments around it have been rendered already. There's no way to do that, right? Because we don't know we don't even know whether the fragment we're working on right now is going to be the pixel. You know, we could actually be rendering something that's about to get covered up by something else. So the more that we do with these bits and pieces, the less sure we're going to be that the other fragments are going to be rendered. And even if we just go, okay, let's just say that we have a scene with nothing in front of it, just a flat image that we're rendering, we still don't know what all the other fragments are going to be, because we're just going to be rasterizing, right? We're going to be going through one line at a time, which means we're never going to know what's in the pixels below us, even if we knew what was in the pixels above us. So the beauty of post-processing is we've finished with that. We've gone through our normal fragment shader and we've written color values to all of the pixels on our screen, and then we can read them. So the kernel can then read from all of the other pixels on the screen because we know they've already been finalized. Finalized, maybe not the perfect word for that. They've been rendered, and then we're doing our processing after that render. So yeah, now we can access the other colors on the screen, which is really nice. So a really simple kernel effect here, this is one I took from LearnOpenGL, took their exact numbers from there, is if we take the pixel and we take the 8 pixels around it, and we take all of the values of the colors from these 9 pixels, multiply them by a particular ratio, and then add them together, that's what we're going to get in the pixel in the middle. So this pixel in the middle here is going to get, this is divided by 16, 1/16 of the color of this pixel, 1/8 of the color of this pixel, 1/16 of this, 1/4 of its own original color, and then it's going to get rewritten as a new color that is all of these added up. A lot of the time when we're doing kernel effects, we want to be careful, because what we're usually doing with something like a kernel is we're reading from all of these pixels and writing into the final frame buffer. So we often don't have another intermediate step. We're just dumping this into the final frame buffer, which is why a lot of kernel effects are really careful to add up to 1 exactly. So if I take the ratios of all these pixels and I made these numbers too high, or I didn't divide this by 16, I'm going to end up with a number way beyond 0 to 1. So to keep it less than 1, what we do is we make sure that if I'm adding up something from this pixel, something from this pixel, the maximum possibilities, if all of these pixels were a maximum of 1, there's exactly kind of the ratio here, exactly 16 out of the 16 here. So if all of these pixels were 1, this pixel would be 1. So if it's pure white, it would be pure white. But any less than that, and we use all these ratios to get a particular color in the middle. So this gives us a reasonably simple filter that we can do on every pixel in the scene to blur it. So each pixel is now not purely the color that they are. They're now that color mixed with the colors around them. So we get this thing where, I don't know how well you can see it, especially because I'm not like native resolution for these images, but this goes from a sharp image to a blurred image, because there's no hard edges on any of the objects anymore. They're all just kind of a mix of the colors around them. So this is a simple kernel effect. It only takes the adjacent pixels, but you can definitely take more than the adjacent pixels. So we can also go to more complex kernels. So we can be like, okay, this isn't just the 8 pixels around it. We can make different shapes. This image is here just to explain what bokeh is. Bokeh is a particular effect that comes from physical cameras, and it's an artifact of being out of focus with a particular shape of lens. So you'll see bokeh like this. So this is real bokeh, so this is physical camera bokeh, and the lens on this physical camera is roughly round. You will see bokeh in other from other cameras that's like a hexagonal shape and things like that, and that depends on the shape of the aperture of the camera. So when it goes out of focus in a particular way, the shape of the aperture actually changes the way the lights in the scene end up imprinting on the film. So we're going to do this sometimes in a post-processing effect, where what we can do is we can sample bright spots in the scene and have them expand outwards into specific shapes, and we do that by shaping the way that we sample the kernel into the other pixels around it. So we can do some really, really cool stuff with these kernels. What we can do is now expand our capability to use other parts of the scene that's already been rendered. So let's look at a specific example of this, which is bloom. So I would call this like a mildly complex post-processing example. I'll talk about other things that are even more complex than this at the end, but I thought it's good looking at the clock. I've got enough time to really talk about this. So bloom is an effect that uses HDR that we did in a previous lecture, but it also goes into post-processing of that HDR to mimic the idea that, like, when you look directly at a really bright object, it appears kind of larger than it is. If you look directly at a light, you don't just see the filament in a light bulb. Sorry, I'm just showing my age. Very few light bulbs nowadays have a filament. But you don't just see the little fluorescent tube of the light bulb. What you see is the light kind of emanating from it, and the light appears bigger than it is. And that's this bloom effect, is the light kind of bleeding outwards into other things. When we're rendering things in 3D graphics, we tend to just render exactly where the pixels are, not necessarily thinking about the expansion of the light going out in different directions from a light source or from a highly reflective object that is reflecting like the sun or something like that. So bloom is something that we understand and we intuitively believe in, but we want to make that happen in our rendered environments. So how are we going to do this? We're going to start with the HDR that we did previously. So we're going to write to the HDR frame buffer. So we're going to actually have multiple frame buffers here now. So we don't just have the final render of the scene and then the main frame buffer that goes to the monitor. We're going to have the HDR frame buffer. So remember that when we wrote to the HDR frame buffer, it was a floating point frame buffer. It wasn't clamped between 0 and 1. It was able to contain much larger possible light values. So instead of going straight into the HDR algorithm and applying the tone mapping, which brings it down to the 0 to 1 range in a particular ratio, and then just sending that to our main frame buffer, we're going to do a little bit more to this beforehand. So we're going to make another frame buffer. So we've got like 3 frame buffers now. We've got the one that's going to the scene, we've got one with HDR content, and another one which I'm going to call the bloom buffer. It doesn't have a particular name. And what I'm going to do is I'm going to copy light values from the HDR frame buffer. So the HDR frame buffer, I could actually go through and read any sections of the HDR frame buffer that have a light value greater than 1. So they've gone into the high dynamic range. This light is technically more light than the scene can handle. And we're going to copy only the light values that exceed 1 into this bloom buffer. So the bloom buffer is going to be mostly black. It's mostly just zeros. So actually we'd have to set it as zeros first. So mostly black. But then anywhere there's a super bright light, that's going to have its color. So it's going to look a bit like this. So we've got this scene here. This scene has been built intentionally with a few light sources that go beyond the low dynamic range. So if we've got these high dynamic range light sources, that means the light values where these sources exist, so these are probably emissive, I guess here, is greater than 1, but also where they're casting light, so the white one I think is the brightest, its reflections off parts of these objects. So you may recognize the specular box, the partially specular box that we've seen previously, reflects light here, and even the floor reflects light here at a value greater than 1. Most of the other parts of the scene, it's only the kind of emissive light sources that are greater than 1. So what we've gone through is we've taken this HDR frame buffer, found any values greater than 1, and copied them directly into this bloom buffer here. And so the bloom buffer is quite limited, actually. It's only got light sources in it. It doesn't have any of the other geometry, except when that geometry is really reflecting a lot of light. Then, excuse me, there's a reason why I taught you a specific sequence of different things. I can now blur this. Alright, so I taught you HDR and blurring just so that I could teach you bloom. So we can use the blur we showed earlier, but then I'm probably going to use a bigger blur than that, because that blur could only send color data into adjacent pixels. And that's not really going to bloom very much. It's going to be the tiny, tiny bit of bloom that you're never going to notice, but we can use a much bigger blur. For example, we might use this Gaussian blur. So I found the actual numbers from a Gaussian blur. There's a mathematical formula for this, right? This isn't just memorized numbers. But if you've got a lot of spare memory and you want to save mathematical processing time, then you just chuck this into RAM and sample from it. So you just take these and multiply these things out. I haven't verified it, but I'm pretty sure that all of these numbers add up to 1.0 here. So what we're doing now is we're taking a wide range of pixels for every pixel, which means that this light is capable of blooming pretty far away from its original geometry, which is what we want this thing to do. When we think about the number of pixels we have on our screen, this going 3 pixels out from the original pixel is not even very much bloom. It's hardly noticeable. The real blur that we might use to get this far away from these things might have, like, 30 or 40 pixels. There's many different possible kernels we can use here. The end result of how cool your bloom looks is going to be based on what you did. Probably with this blurring effect is the most important part of this. So what we're doing really is we're taking everything that has HDR greater than 1 and we're expanding its influence over the scene out into pixels beyond what it originally had. So it blurs out and goes beyond those pixels, and so now our bloom buffer is has more influence of the scene than it had originally. Okay, the next thing that we do is we add the bloom buffer back to the HDR frame buffer. And we've got to be a little bit careful here, because like a lot of the times when we add this back in, it's going to double the light in each of these places. But the more important thing is, rather than just doubling the light in the places that it was greater than 1, the important thing is anywhere where it was greater than 1, the light bleeds out into other pixels. So now I think, yeah, this green one here is a really good example of this, where it glows, and that glow is kind of reaching us beyond the edge of this block, which is otherwise blocking that light. And this red one here also is encroaching on the geometry for the blocks around it, which would otherwise be obscuring it. And it gives us that kind of feel of looking at something that's so bright, it's just kind of getting beyond, like it's sort of overloading our eyes in a sense. Oh, Hamish is like, so if we look at a light with bloom and then it slowly gets covered up, the bloom won't extend beyond the object. It just gets removed once the light itself disappears. Yeah, so in this red one here, if this red one moved directly behind this object, we'd probably lose it. In the real world, with enough dust in the air and things like that, we'd probably still see that red object. It's nearly like its light's not curving around the object, but it's reflecting off dust around it. We'd still probably see it. This being a screen space effect, being post-processing in the screen space, we can only work with what we can see on the screen. We don't know that there's more geometry with this light behind. We may have some evidence of it with the light reflecting off other things, but we won't know for sure. So there's no way that a screen space effect like this can know anything about the geometry deeper in the scene. So yeah, those are the little drawbacks of something like this. But either way, we're getting a really cool effect here, where what we can do is we can say, all right, we can get these like high dynamic range lighting areas to then go further than the size that they currently are. And you can do some really cool stuff with this if you change your blur filter. You can get lens flare effects from these. So you can actually just go, okay, this one, because it's over, like it's really, like this one I think is the brightest in this scene. It's really far beyond 1. You can have different ranges, and this thing could have like just like a shaft of light coming out the top and the bottom of it because it was so bright and stuff like that. So there's lots of cool things you can do with stuff like bloom. So this is a really simple example of how to do it. But I still would consider this to be a sort of a complex post-processing effect, because what we've done is we've done one processing effect, which is the HDR frame buffer, and then we've done a second post-processing effect to apply a blur to any sections where the HDR is above a certain amount, and then we've recombined those effects and put that into the final frame buffer, and that's the thing we see in our scene. We can do multiple of these effects at once, so we can turn on a whole bunch of these things, and you just got to be careful of the order you do them in. So I could do this light bloom thing, and then after I do this light bloom thing, I could then go to a black and white filter. So yeah, there's light bloom, but it's gritty. This is the light bloom from the street lamps in the rain in New York in the 1940s, you know, like that kind of thing. So there's a lot of other post-processing effects. So I've just got enough time left to talk about some of these and how they fit. So I wanted to talk about motion blur because I know that everyone loves motion blur, and everyone was talking on Monday about turning off motion blur all the time. But I still think it's worth looking at because motion blur gives us a temporal effect, a time-based screen space effect. And this is quite a complex one because what this involves is not just saving a frame buffer of the render of the current scene, it saves a frame buffer of the render of the previous frames as well. So we can go back, say, 5 to 10 frames in the past, or if we want to do this in a really specific way, we don't go in frames, we go in time. So, I don't know, a quarter of a second ago, if you want to get really extreme, with a quarter of a second is a long time for motion blur. But, you know, a tenth of a second ago, a 20th of a second ago, or something like that. And you take these previous frames, and instead of blurring just with the pixels around you, you blur with the past. So I blur between, so this is then called a kernel filter, which has when you add dimensions to the kernel. So we have the present, one previous frame and another previous frame, and if we pierce through those and we say, what color is my pixel now? What color was it previously? What color was it before that? We blend all of that together. And if we blend all of that together, we get a blurring of the colors that were there in the past and the colors that are there in the present. So this is kind of interesting because then what we will get is anything that changes its color quickly, so things that are moving, are more likely to then get this blurring effect happening. Things that are stationary in the scene are going to be the same in the present as they were in the past, so they're not going to have this effect applied. So this is kind of cool. Again, it's nearly like everything that I tell you, every effect that we're going to do is going to take more graphics memory and more time to process. Post-processing doesn't usually take a huge amount of processing time though, because even though it's going through every pixel in the scene, again, it's not going to have to do like multiple things for fragments. It doesn't have to do things with vertices or anything like that. It's just pixel colors. So it tends to be a lot quicker. Like the simple blur like this that samples from 8 numbers and adds them all together. That's pretty simple. There's not that much work going on. So you take this number, multiply it by a 16th, this number, multiply it by an 8th, and you just sum them together and it works. So it's very little processing time compared to, you know, a lighting effect with a fragment shader, that kind of thing. The bloom obviously takes more because you're doing this multiple times. So you do the HDR loop, you do the create the bloom buffer, blur the bloom buffer, copy it all back in. So you've got like, 4 times the number of pixels. Still not huge, still not that bad. The more complicated your blur effect is, the more pixels it has to read from. But even then, pixels are pretty local in memory. Like, you're going to be able to grab multiple pixels at once, knowing that your kernel filter is probably going to use all of them at the same time. Yeah, and another thing that we use is this thing called ambient occlusion. I think that a lot of people, if you're playing modern games, everything, I would think in the last 10 years and more recent than that, most all of those will do screen space ambient occlusion. And this is a thing to make up for the fact that our basic Phong model doesn't have a really good ambient lighting model. It has a blanket solution to ambient lighting. And what that doesn't give us is the idea that when objects are close to each other, when objects are very close to each other, they kind of cast little shadows on each other. They don't cast direct lighting shadows, but they cast little shadows, and they just kind of obscure each other from getting all of the ambient light, because the closer things are to each other, the less chance ambient light has of passing through objects, in a sense. So what this uses is it uses our depth buffer and the surface normal at that fragment. So what we actually have to do for this is, while we're rendering, we don't just take the screen, but while we're rendering, we write out a little bit more information than we would have otherwise. So we write to another buffer, and that buffer is going to store the depth information for the fragment as well as the surface normal currently at that fragment. And those two pieces of information allow us to see if, say, 2 fragments next to each other have very different normals, and at a roughly the same depth, means that they're in a corner together. So they're in like this kind of corner shape or something, because their normals are different but their depth is similar. And when we get those situations, what we'll do is we'll artificially darken those areas. So areas in corners, like these minute shadows things cast on each other, will cause this thing called ambient occlusion. So what we do is, like, when things are close to each other and their normals aren't the same, then we darken them a little bit. If their normals are the same, then we think that this is a flat surface, so it's going to pick up all the ambient light. If their depth is different, then they're not going to affect each other. So my hands can't cast any shadows on each other, or little ambient shadows on each other right now because they're so far apart. But if they get close together like that, there's going to be ambient shadows in the middle here where my thumb is. So ambient occlusion uses all of that kind of stuff. And again, like other things, it's going to cost more processing time to do it. Anti-aliasing I put in here because I realized we only have 1 week left in this course, and it is a reasonably important effect, but I'm not going to have time to teach it to you. I may a little, but I think now that I've covered it here, I won't. But it isn't really a post-processing effect. I threw it in here, but it tends to be calculated before post-processing. So it tends to be calculated, I think if you look at the default OpenGL for anti-aliasing, it's processed in the fragment shader. So what anti-aliasing does is it says that if I have like a diagonal line going across my screen, I'm only ever approximating that diagonal line, because all of my pixels are basically squares. So I've got a row of squares, and then I go down a row, and another row of squares, and go down a row. So instead of this smooth diagonal line, I've got a series of horizontal lines. And every time there's a corner and a drop, that's visible. And this really depends on how high quality your monitor is. But we can calculate that so that instead of getting a harsh line and a drop, we get a fading of color and a mixing between the background color and the foreground color where that jagged line is, and that can smooth out that line. It's not necessarily a post-processing effect, but if you want to manually implement something like anti-aliasing, or you want to do specific anti-aliasing effects, you can do it with post-processing. And there's a whole bunch of other stuff. Depth of field. Having things at different depth go in and out of focus. So we can apply a blur filter only to things that are outside of the focal depth. So again, we'd use depth buffer information there. We can do color grading. Color grading actually makes a huge difference to the personality of a scene. And chromatic aberration, which is like dealing with shifts in color. I think chromatic aberration originally was a simulation of the way film changes the color of things while it's being processed. Oh, Matt's saying that, yeah, heaps of modern games are using post-processing anti-aliasing. Yes, deferred rendering. I left that off this list because deferred rendering I actually want to cover with a bit of time rather than just like 5 minutes at the end of the lecture. Okay, so that's an intro into post-processing. And I've gone a little bit over time. I apologize, but I tried to squeeze in a lot this lecture. So today, what did we cover? We looked at planar reflections. We looked at a lot of the ramifications of planar reflections and a lot of the ways that we may implement them. And then we looked at the fact that no one does. And not no one. The Need for Speed game 100% had planar reflections. Like it had that the ground surface with the water. So that was a normal mapped planar reflection. Also, there was potentially it was potentially using the specular map of the road to decide which bits were reflective as well. So there's heaps of stuff going on in that particular game. But then I could reel off examples of many games that just ignore reflections entirely and just like the gameplay does not require us to reflect any light or images. And then we looked at post-processing, which is expanding the idea of the render to texture and the frame buffer stuff to do things to the scene after the frame is rendered. So there's a lot of really cool stuff that you can do there. And that, I think, the post-processing, I think, is when that came into effect, when that started happening, I think, I want to say this century, it really changed the polish level of a lot of games. Like you look at certain old games that just started just putting a film grain effect, just messing up the pixels in the scene. It's interesting to see how the immersion and the cinematic feel of games started really appearing at that point in time. Because I think that one of the best things that post-processing can do is to trick us into feeling something. Even though a lot of the things that post-processing are not even really rendering the scene, they're just altering it in a way. But it's been of great value to games over the years. Okay, I definitely should wrap it up there. It's like 12:04. Okay, I will pause it here. If anyone has any questions, they want to ask details about how different post-processing effects work and stuff like that, feel free to put your questions in chat. I'll come back in a second. I'll answer any questions that have come up. Okay, I'm back. I don't see any questions there. Maybe I've explained things so well. Oh, Kaichi just woke up. That's okay. What time is it for you now? Like it's 9 a.m. or something? I don't think there are any post-lecture questions at the moment. We took a look at post-processing today, Kai. Well, also planar reflections, but post-processing was the fancy bit. the completely new technique that we're showing here, which is not super new, really, when you think about it. The tools with which to do things were already there. Koresh is too worried about the assignment to digest all the lecture material today. I understand. I understand this being the last lecture before the assignment. The assignment's only due in 2 days. That there's a fair bit of work to be done. I guess I should give you the general spiel that I usually give about assignments. Is remember that passing a course only requires you to complete 50% of the assessments. So it depends on how hard you want to push the bonus marks that you're looking for in the course. Because anything above 50 is technically a bonus mark. I've had cases where I've done, like I've learnt courses, and I know that I've gotten a really good amount of information out of the course, but I haven't had time to actually be assessed completely on the amount of stuff I know, so I'm just sort of like, that's fine. I got what I needed out of the course. My marks don't necessarily reflect it, but it's okay, because in the reality of it, if I want to reuse what I've learned from that course, I do have enough to be able to do that. So there's always a bit of a back and forth. We always have to decide how much effort and how much time we have to put into looking good in the course versus being happy with what we learned from it. Assignment 3 is going to get even worse like that, because A, it's at a difficult time of term, and B, there is kind of no intention that anyone's capable of getting 100% in assignment 3. Like assignment 1, is like, I expect a significant percentage of the course to get 100%. Assignment 3, I'm expecting 0 to 1% of the course to get 100% in that assignment. So, which I haven't finished writing yet, so we'll get to that when we get to that. But again, assignment 2 is on that scale as well. Like the average mark for assignment 2, I'm expecting to be much lower than the average mark for assignment 1 by sort of 15 to 20 marks, I guess, depending on how many marks you got in general. So it's that kind of thing where to accurately assess everyone across this idea that I can say to some people that they have learnt everything possible that I taught in the course, and I can say to other people, you've learnt enough to have a good basic understanding of this thing. So for example, someone can pass this course, happily pass this course without implementing any post-processing at all, and I think that's fine, because post-processing is cool, but it's not core to graphics. If they are unable to render geometry, then they shouldn't be able to pass the course. So that's the kind of the scale that we're on. Oh yeah, you're saying you're actually more okay with assignment 3, as it's probably due in week 12, I think is when I'm planning on making it due, which is, because you don't have any final exams, so you can make up marks in assignment 3 that you couldn't get in assignment 2, potentially. Yeah. And I apologize that, there's a lot of assignments due at the moment. I tried to at least make it due week 9 instead of week 10. Because I know that most courses will have, if they have 2 assignments during term, it'll be like a week 6-ish due date and a week 10-ish due date. And I pushed both of mine earlier to try to get out of that standard cycle of assignments so people aren't overloaded. But it's hard to do. It makes so much sense to have them due in week 6 and week 10, because it's you teach them stuff, you give people a few weeks to show what they know of that stuff, and that's the due date. And when you've only got a 10-week term, there's really only a couple of places you can place those due dates. Jeffrey's saying, so rendering geometry weights more. I guess so, because the way that we would scale a subject, in a sense, is that I don't want the subject to be scaled over 0 to 100. If I scale the subject over 0 to 100, then 50% of the class fails, and that's not even remotely correct. Because if I was to just kind of talk to everyone in the class, talk to everyone individually, there's no way that I would say that 50% of the people who are currently attending the class were so bad at this course that they needed to do it again to learn it, right? So what I need to do actually is I need to make sure that there's like nearly 50 marks of the course are there for basic competency. So basic ability to do rendering, in a sense. So what I need to do, that's why assignment 1 and parts of assignment 2 are bumped up for the simpler things. And so some people who are like, people who are really on top of the subject material are going to be like, why are there so many marks in really easy things? And it'd be like, it's not really the way I would say it. It's not so many marks in really easy things. It's a focus on core competency. So the things that you really need to know to be able to do graphics, the things that are building blocks that other things are made out of, they need to have the big marks to make it so that if people understand those core concepts, then I say they've passed. So those core concepts get you 50% of the course. And then think about all the stuff I've added on top of that. So some like really little thing like blin-fong lighting, or another thing like post-processing. That's cool to have. But there's also other things that are cool to have, like, can you do certain forms of animation? Can you do multiple mapped objects? So not just a texture, but a specular map and other things. Can you do reflections? All of those are squeezed into the rest of the marks. So each one of those has a certain portion of the marks attached to it. And it's like, if you get 100% in this course, it means you've implemented everything that I've spoken about in the lectures. And that's a whole lot of work. That's a stupendous amount of work. Because heaps of things I've talked about in lectures, like this bloom effect, I only talked about like for 15 minutes. And we're definitely not going to have that, like completely implemented for you in source code in a tutorial. Like that's way too much to hope we could have that. Oh, maybe, I don't know. I think, Matt, are you writing the week 10 tutorial? I can't remember exactly which effect that we're going for, but it could be this. So yeah, if it is this, then maybe I'll assess you on a different kind of post-processing or something. So if people want to get 100 in a course, they've got to be able to take what's taught in the course and show that they understand it so well that they can do stuff with their learning that I haven't even taught. If someone's looking for, say, a credit distinction level in a course, then it can be like, I can do everything that was taught to me in the course, and I can do it without making mistakes. If I'm looking for a pass, it's like, I can do the core things in this course, but there's a bunch of things I didn't pick up. But that's okay, because all of those things felt like they were add-ons, I saw some chat in the Discord. People were talking about... Oh, Simon's writing the week 10 one, yeah. I remember we had a vague plan. I was like... outline the plan in our tutor meetings, and then like a few days later I have written 2 lectures and I can only remember what's in the lectures and not remember what was in the tutorial plan. It's pretty funny. So yeah, what was I saying? Yeah, so the mark scaling always looks a bit like that. So the way that's going to end up looking in terms of your assignments is that assignment 1 had a whole lot of core in it. So the expectation was people get nearly all the marks in assignment 1. Assignment 2 is a mix of core and extension techniques in a sense. So I'm expecting like someone who's going to pass the course to still get a reasonably high mark in assignment 2. Like they still could get a mark in the 70s in assignment 2. And if you get 100% in assignment 1, a mark in the 70s in assignment 2, you've actually already passed the course. That adds up to roughly 50% of the course. So that's how I designed the assessment. So... the thing that happens then is assignment 3 has basically no core in it. Assignment 3 is all extension work, which means you can get 0 in assignment 3 and still consider yourself a competent enough student to understand what's happening in this course and understand enough that you could learn advanced techniques later. But if you want to go into like distinction, high distinction, or 100% of territory, by the way, I should point out, like, for me in my university career, I never 100%ed anything. I got like 1 mark in the 90s ever in my career. So don't, unless you've got like this proven track record of being able to ace subjects like that, don't try. It's just, you're just going to burn time and burn your own mental health on behalf of that. So assignment 3 is not designed for people to pass that assignment in a sense. It's designed for people to show a high level of capability in this subject. Because you think of it, assignment 1 is like your participation marks and your ability to do basics. Assignment 2 is piled on top of that, so that pushes you to a passing mark and even above a passing mark if you do well enough in those two. That's core competencies, the basic lighting algorithm and working with geometry and stuff like that, that is necessary for all the other things later to be understood. And assignment 3 is on top of that. So if you want to get a distinction, like you can get a distinction in the course while failing assignment 3. You know, because if you did really well in the first two, you're already at 60, which means you only need like a third of the marks of assignment 3 to get a distinction in the course. And that's how it will be kind of put together. That assignment 3 is going to be like, can you do cool stuff? I call it cool stuff because we're getting to the point where we're doing like Bloom and stuff like that, where you can see in the course how at the beginning of the course it was like, let's build up the idea of how to do things. And at the end of the course, it's like, we are literally doing the things that is in the computer games that we play. And so we get excited about those kinds of things. That's why I call it cool stuff. And so assignment 3 is like, can you do cool stuff? And I know people have been doing very, very cool stuff in assignment 1 and 2. The Flex channel's been quite busy and stuff like that, which is really good. But yeah, so that's how I designed my assessment curve for this subject to be like, what does it mean to get a pass mark, or what does it mean to get a credit, a distinction, and a high distinction? And the assessments reflect that in a sense. So third assignment, that's why I think I put it in the course outline that the assignment 3 was called Show Me What You Got. I can't remember if it actually was or it wasn't. I like to sometimes take things a little bit seriously, and then sometimes be like, you know what, things are gotta be like interesting as well. Yeah, show me what you got. Also considered a 2-week take-home exam. I'm actually expanding it to a 3-week take-home exam. Yeah. So showing off all the skills you've learnt or explored during the course. And that's going to include, can you do things beyond what I taught you? So, for example, if I had not taught you entirety of Bloom, but I've taught you HDR and I've taught you blur, so there's a blur effect there, and HDR that I taught you previously. If someone then implemented blur in assignment, if this wasn't this case that I'd actually just taught you the entire process, but if someone implemented blur in assignment 3, I'd be like, yeah, there's marks there for that, because you've taken techniques we've taught you and you've been able to expand on them just one step further. You know, that's the kind of thing that gets marks. And that's the kind of thing that you expect from, that we as a university expect from anyone who wants to get a high distinction. Someone with a high distinction should be able to take our teaching and take it further than we've taken them. Because a course takes you along a road, in a sense, a road towards knowledge. But we get off at a certain point. So the bus drops you off and it goes back to pick up other people to take them along that road, right? The courses do. We bring you to a certain point, and whether you can keep going in the same direction is kind of the high distinction student. Whether you got there on the bus and you know where you are is kind of like the pass to credit student. If you got off the bus before it got to the end, then that's the fail student, in a sense, where it's like, unfortunately, I don't know, often it's like, I just didn't have time this term for this, and so I don't know where the bus actually went, you know, and that's fine, because the bus comes back, you can get on it again. So if you're still interested in stuff and you happen to have failed, it's never really the end of the road. You can go back, get on the bus again. There's another bus coming that can take you to that knowledge place where you want to end up. Anyway, that was an interesting dive into assessment scaling and sort of, I wouldn't even call it educational theory. I don't think anything this has got to do with like pedagogy, which is like the study of like, you know, transferring information to people, I guess is the best way to say it. This is more about like navigating the meta of UNSW's assessment system, because that's really what it is. Other universities are going to assess in different ways. We have this particular expectation, this particular scaling that we're going to use for things. All right, I'm going to wrap it up there. It looks like there's no technical questions here. And I should go get some lunch. All right. see you all soon. Next time I see you, hopefully you will have gotten through the hurdle that is assignment 2. And I will also, hopefully, next time I see you, I will have released assignment 3 as well. And you will, you'll have an idea about the challenges ahead of you for the rest of this subject. All right. See you all later.